Hi, my name is Muhammad Wafi bin Aziz. I will present my final year project, which is synthesis of nickel-rich doped with titanium and molybdenum as a cathode material and their electrochemical performance. This is assisted by Dr. Muhammad Firdaus Kasim. Today, I want to discuss the importance of electric vehicles in reducing carbon emissions and improving air quality. With a high number of registered vehicles in Malaysia, EVs offer a sustainable solution by producing zero carbon emissions. EV also contribute to achieving net zero carbon and improving air quality in the cities. Major car brands are competing to produce high-quality EVs with longer driving range. The driving range depends on the battery use, and lithium-ion battery have become key in the success of EVs. However, the cost of EV is still high and research is needed to improve the driving range and to lower the cost. The cathode materials in lithium-ion battery contribute significantly to the battery's cost. Researchers are exploring nickel-rich cathode materials for their lower cost and their performance. By modifying cathode material, we can enhance driving range and lower the EV cost. Challenges related to the performance degradations and safety concern must also be addressed. In our research, we aim to synthesize nickel-rich cathode material using a co-precipitation method to overcome the structural instability with dopants like titanium and molybdenum. Our focus is on investigating crystal structure and morphology to improve lithium-ion battery performance. Through our efforts, we hope to enhance the battery performance and extend the battery life and makes EVs more affordable and practical. This research is crucial for a sustainability transportation future. Exciting progress has been made in developing cathode material for lithium-ion batteries in use in electric vehicles. Researchers have formulated a lithium-nickel cobalt with reduced cobalt content to address a cation mixing. A common issue in nickel-rich cathodes, foreign elements are being introduced to the crystal structure. However, further research is needed to achieve a pure and single-phase structure. These advancements bring us closer to high-performance batteries, improving the EV range and sustainability. Today, I am excited to share the latest research advancements in ultra-nickel-rich cathode material, particularly lithium-nickel 0.9 for high energy density in lithium-ion batteries. These materials show great promise in improving the performance and sustainability of electric vehicles and the energy storage system. To bring these materials from the lab to the market, further research is needed. The focus of this work is to study the effect of titanium and molybdenum dopants in the cathode structure. By introducing these dopants, researcher aims to enhance the structural and the electrochemical properties of the cathode. This investigation will provide valuable insight into the potential of dopants modified cathodes, benefiting both academia and the industry. The outcome of this research have significant implications. Optimizing cathode design and composition will lead to higher energy density and improve the battery performance, extending the driving range of electric vehicles and promoting a cleaner and more sustainable future. Through dedicated research, we are pushing the boundaries of battery technologies and accelerating the adoptions of advanced energy storage system. The objective of this research is first to determine the purity of synthesized pristine nickel-rich lithium-nickel 0.9, titanium and molybdenum doped. The second is to determine the morphology and crystal dimensions of the synthesized cathode material using field emission scanning electron microscope. And lastly is to examine the elemental composition of cathode material using energy dispersive X-ray. In the late 70s, global scientists began developing rechargeable batteries. Professor Stanley Whittingham case for a fast-charging battery during the oil crisis led to initial attempts with titanium disulfide. Safety concern arose, but John B. Gordon's introductions of lithium cobalt oxide showed the promise. Finally, Akira Yoshino's use of petroleum coke created the first prototype of the lithium-ion battery. Let's take a closer look at lithium-ion batteries, which have revolutionized portable powers. Lithium-ion battery consists of essential components, which is an anode, cathode, electrolyte separator, and 2 current collectors. During charging, energy is stored as lithium ion move from the cathode and the anode through the electrolyte. When discharging, the stored energy powers a device as lithium ion move from the anode to the cathode. This movement of ion create an electric current, making a lithium-ion battery a reliable and rechargeable source of power for various devices. Doping nickel-rich cathode material with additional element is a strategy to enhance their structural integrity. This process helps prevent John-Taylor distortion and maintain the layered structure during charge and discharge cycle. Doping restricts Li ion, lithium ion or nickel ion mixing, preventing oxygen evolutions and increasing the cation disordering formation energies. By introducing positively charged impurities into the crystal structure, cation doping plays a vital role in optimizing the performance of this cathode material. The co-precipitation method is a cost-effective and scalable approach for synthesizing cathode material used in lithium-ion batteries. This method involves mixing metal precursors with solvent to form metal hydroxide precipitate, which are then dried and calcined to obtain the desired cathode material. Common cathode materials synthesized using the co-precipitation method include lithium cobalt oxide and lithium mangan oxide. The co-precipitation methods offer simplicity, low cost, and the ability to produce highly pure and homogeneous material. However, materials synthesized through co-precipitation may exhibit a poor electrical conductivity, which can impact battery performance. The performance of lithium-ion battery made with the co-precipitate cathode materials depend on various factors, including the quality of the cathode material itself and the battery design. Cathode material that synthesized via co-precipitation may typically exhibit a good capacitance and energy density. However, their electric conductivity may be lower compared to material synthesized through other methods. Optimizing the performance of the batteries made with co-precipitate materials involve controlling the synthesis process to achieve purity and homogeneity while also optimizing the battery's design and construction. I would like to provide further details on the synthesis process for lithium nickel 0.9, cobalt 0.1 and the titanium or molybdenum doped layered cathode materials. The starting materials or dopant are mixed with NaOH and then stirred. NH3 is added periodically until the solution reaches a pH of 11. The resulting solution is then filtered and dried overnight in an oven. The precursor is then subsequently ground and sintered at 480 degrees Celsius for 5 hours. After that, we grind it to a fine powder and then lithium was added. The final step involves annealing the material at 920 degrees Celsius for 15 hours. This comprehensive process ensures the desired structure and properties of the synthesized cathode materials for advanced lithium-ion battery. I would like to present the finding regarding the synthesis of lithium nickel 0.9, cobalt 0.1 with titanium or molybdenum dopants. Initially, we attempt to achieve a pure compound using a lithium carbonate precursor. However, despite adjusting the ratios, the desired purity was not obtained. After consulting with Dr. Firdaus, we decided to substitute lithium carbonate with lithium hydroxide for the titanium doped sample. This modification led to the formation of a pure compound. For the molybdenum doped sample, we continue using the lithium carbonate and it resulted in a pure compound as well. In summary, our research demonstrates that using lithium hydroxide as a precursor is more effective in achieving a pure compound and single-phase structure in nickel-rich cathode material. This structure closely resembles lithium cobalt oxide, which is important for battery manufacturing. This finding contributes to the understanding of the best lithium source for optimal battery performance. Through the analysis of the crystal structure of the MO dope compound, which is E, we observe a significant finding. The RIR value for compound E was higher compared to other compounds. It is important to note that an RIR value that higher than 1.2 indicate a low cation mixing, leading to favorable cation ordering and excellent electrochemical properties. Based on these observations, we can conclude that compound E with molybdenum as the dopant exhibit the most promising result in our synthesis. Its superior crystal structure suggests improved performance and enhance the electrochemical properties. The SAM and EDS analysis on the 1% molybdenum sample E revealed some interesting findings. The nickel and cobalt content were lower than expected, while the molybdenum content was slightly higher. However, the molybdenum content obtained experimentally aligned well with the calculated stoichiometry. The distribution of elements was not perfectly homogeneous, with some elements exceeding expected atomic concentrations and others falling short. Further research is needed to understand and improve the material's homogeneity. The mapping analysis were done for 1% molybdenum dope sample E to see the elemental distribution throughout the sample, and the spectra are shown in the figure. From the mapping analysis, it can be concluded that the elements are well distributed. In conclusion, dopant included titanium and molybdenum were used, which the doping level was set at 1%, and based on the result obtained, both showed the positive result and had the potential of reducing the cation mixing that are having by lithium nickel cobalt as a cathode material. Overall, this dopant was successfully synthesized via co-precipitation method. For future study, battery testing must be conducted to observe the capacity, cyclability, and the battery's lifetime.